Hi, my name is Tiffany and I'm one of the electrical and computer engineers on the team.
My name is Sarah and I'm one of the systems engineers on the team.
Hi, my name is Christine and I'm the biosystems engineer on the team.
Hi, I'm Gianna and I'm a systems engineer.
Hi, I'm Anthony and I'm the other electrical engineer on the team.
Hi, my name is Dustin. I'm the mechanical engineer on the team.
This project was requested by the zoo as they found it difficult to provide enough enrichment for their animals.
The AEA system was designed for the jaguar enclosure with 4 units placed throughout the habitat.
What is animal enrichment?
Hi, my name's Stephanie and I'm the Animal Welfare Specialist here at Reed Park Zoo. Enrichment is the process of improving an animal's habitat by providing different stimulation, which encourages the use of their senses and natural behaviors.
Reed Park Zoo wanted our team to automate this process to increase the amount of enrichment and better the lives of the animals.
In the early stages of the project, we met with our sponsor to define their needs and developed our functional requirements and ConOps based on those needs. We then developed system-level requirements to achieve our functional requirements and started to consider a solution. For our solution, we knew we were going to use a sensor that is able to detect animal motion and considered 3 different types of sensors we could use. After further analysis and discussion with our sponsor, we decided on the PIR sensor as it was proven to be a good device for wildlife tracking and is the easiest to adapt into the operating environment than the others. Another trade-off analysis we conducted was of 3 communication systems to decide which one we wanted to use for our sensors. Ultimately, we chose the individual communication system as it allows for easier communication between the sensors and more control over the individual sensor subsystem units. Based on these design considerations and further research, we were able to derive our system-level requirements into subsystem-level requirements and the related components. With these components we conducted analyses and further validated that these components will meet the requirements. We then decomposed our requirements into a verification plan that highlighted how our requirements will be tested. With this, we created our prototype plan and began implementation.
The first PIR sensor we selected was HCSR501 and showed problems in early testing. The PIR sensor was believed to have adjustable distances between 1 to 21 feet, but the sensor did not pass testing, leading us to reanalyze our options. We provided 2 alternative options to our sponsor. After providing insight on each, our sponsor chose the interchangeable option. So we ordered PIR sensors at 3 distances based on the needs of the sponsor. We also designed a flange to our sensor unit in response to the sponsor's concern with wanting a narrow detection range. We then conducted testing with the sensors and flange. We tested at a variety of distances from the sensor and its center line. This allowed us to develop a detection region for each sensor. During testing, the 7.5-foot sensor didn't function, and after discussing with the sponsor, it was decided that this sensor would be eliminated. Ultimately, the flange and PIR sensor worked together to create a narrow detection region that when the animal entered would be triggered and communicate with the software.
Since the jaguar enclosure does not have internet connection that can be used for communication purposes, we implemented a mesh network through the use of radio transceivers. We also implemented an LCD screen and timer to each individual sensor subsystem unit to ensure a proper activation-deactivation period of power input. The timer functionality allows the user to allocate a specific amount of time that each individual activity is activated for and will receive power from the relay. The initial default time is set at 15 minutes and can be adjusted by intervals of 5 minutes, with 5 minutes being the minimum set time and 60 minutes being the maximum set time. The time is saved internally for power cycle save mode. Once the assigned period of time ends, the timer will cue the relay to shut off the power and reactivate the PIR sensor for motion input. There is also a timer included as an internal component communicating with the PIR sensor in its unit. The PIR sensor will indicate if another sensor is activated to the timer. When this occurs, the timer begins a 5-minute deactivation period of its own PIR sensor to ensure that only one enrichment device can be activated at a time. The other sensors will not prompt their timers to relay power to their attached enrichment devices. After the deactivation period has passed, the timers will communicate to their sensors to update their statuses to active and allow input from the animals. All statuses are displayed on the LCD screen.
For powering our system, our team opted to use an AC option due to availability, sustainability, and ability to interchange enrichment devices. The sensor system utilizes a 60-watt AC to DC converter to provide the necessary DC power for the internal components. There are 3 different power rails of 3 volts, 5 volts, and 12 volts. To allow power to enrichment devices, the system uses a 5-volt 240 VAC relay to power on and off the 120-volt AC outlet. Due to our microprocessor being able to only output 3.3 volts, we had to implement the flyback diode circuit. This circuit design ensures that the relay can switch on and off without damaging other components in the system by using the diode to mitigate voltage spikes when switching off.
One of the most important needs from our sponsor was that the system needed to be able to survive Tucson weather conditions, since the placement of the system would be housed outdoors and exposed to the elements. We derived our system level requirements for our system to perform at extreme high and low temperatures and in wet conditions. After analysis of existing weatherproof casings, our team decided to purchase a McMaster car case and make modifications to it for allowing power to be supplied to the system and with a rotating bracket. For testing, our team used a water hose to simulate rainfall rates and a thermal chamber to raise the internal temperature of the system to 130 degrees Fahrenheit. After performing analysis and testing for our ATPs, they both passed with a NEMA 4 rating for the rainfall rates.
From initial meetings with our sponsor, we knew we needed a flexible mounting system capable of being mounted at different locations and with different angle orientations. This was a challenge as the team had no pre-existing system to work off of, nor is this type of system common in American zoos. Our design includes 2 rotating mounting plates that interface directly and rotate concentrically with the weatherproof case. These plates include holes for an index plunger to lock the angle orientation. The case and 2 plates connect to 2 base arms on either side, which aid in the system's rotation and angle locking capabilities. These arms then screw into the mounting base plate. Various holes on the base plate allow each sensor unit to be mounted to the zoo's current mounting system or to be staked into the ground. Issues did arise, such as when our purchased metal arrived in incorrect dimensions, forcing us to alter our design to ensure essential functions of the design remained. In the end, a completed unit weighs approximately 7 pounds.
During the testing and implementation stages, our sponsor provided some new ideas and consideration that would go beyond the original design. The first idea was implementing a laser diode component that would assist the zoo in determining the detection range more accurately. Another idea was integrating a selector switch to allow the zoo to power on or off individual sensor subsystem units. This allows the zoo staff to either keep the enrichment on without using the sensor or use the mode where it requires sensor activation. Our last additional design was including the LED indicators to help the zoo staff recognize the status of the sensor externally.
During our introduction of the prototype to the zoo, we presented our circuit on a breadboard, demonstrating the concept of the timer and LCD screen. We also brought in the weatherproof case to give a visual representation of how we will be placing the internal components inside. During this phase, we had discussed building a perforated board and then printing PCBs for a more compact and clean design. To test the ranges and determine potential sensing locations of our system, we positioned the prototype at different heights in front of the glass viewing area and mesh net area of the Jaguar's enclosure. The PIR was not able to detect through the glass due to its thickness. However, it was able to successfully detect in front of the mesh net.
Since we'd never worked on one of these projects before, we didn't really have any set expectations, but we were really excited to see the results. They were much better than we could have ever anticipated.
Our system lays out a base model for many more improvements and adaptations. The near future potential of this system is the ability to be integrated into other Reed Park Zoo animal enclosures and other zoos across America. The potential for this system to continuously improve and expand is endless. Lastly, we would like to thank our sponsor, Stephanie, our mentor, Heather, our videographer, Jed, and the rest of the Reed Park Zoo staff.